strangely drawn thing. Okay. So, phosphoric acids, you've named them in Gen Chem, but they have phosphoruses with with one oxygen double bonded on it, and then a bunch of oxygens holding them together, and they've got 4 oxygens bonded to them. One is double bonded, and then the non-double bonded ones are where you can have your hydrogens. So yeah, diphosphoric acid. Cool. Esters, they kind of look like carboxylic acids, except instead of having a hydrogen there, you have stuff. So you end it with 8, right? Isopropyl benzoate, so you name the side that's on the oxygen, you name as a side chain, like isopropyl, and then the side that has the carbonyl that doesn't have the oxygen, benzoate. Yeah. Does that make sense? Because the 8 is like the double bond, this guy, and then stuff connected to it, you know? Sort of. It's like the acyl, but this one is this plus this, and then stuff. Alright, let's get through this naming. Fine. Lactones are cyclic esters. So it's cyclic kind of like the other ones, but notice we only have one carbonyl because, well, this is a cyclic ester, not an anhydride, so it's not 2 acids that go into making this. It's just as if you had an acid and then you replaced the OH with like an alcohol or something. So, bam. These guys, lactones. I'm not going to make you name those because naming is boring. Esters of phosphoric acid. Fine. Phosphate. We call them phosphates. Or pyruvate. Phosphenol, pyruvate, phosphate, dimethyl phosphate. Cool. This. Amides and amides. Amides. Oh, okay. Amides, you're just going to name amide, like acetamide, or dimethylformamide instead of formic acid. That's just how you know you've got an amide. You can have them primary, secondary, or tertiary. Lactams are cyclic versions of amides, so that's what you call a lactam. Instead of lactone, it's lactam. And then imides are 2 acyl groups on either side of a nitrogen. So it's kind of like, sort of like the equivalent to this, but with nitrogen. So you could, I guess what you're getting rid of instead of H2O in this case is going to be, let's pretend it's always, wait. H2, and this one's going to have, there we go. Then we're getting rid of ammonia and turning it into keep an H. So kind of the same as the other one, but with nitrogens instead of oxygens. All right. Nitriles, they're going to be, we've already kind of seen these, but that's how you name them, benzo nitrile, you just sort of add that. Ethane nitrile, which is also called acetonitrile. Yeah, they say nitrile on there, or O-nitrile. Which of those is not an ester? Hold up a number. Over your head, because I'm short. Everybody hold up a number. I realize now that, man, I really have to squint to see you guys. Okay, so this carbonyl got an oxygen right next to it, right? This one has an oxygen right next to it, so that's an ester, but it's, so when we call that a lactone, a lactone is describing what kind of ester. So like, a square is still a rectangle, right? Like, if you call a square a rectangle, you're not wrong, you're just less specific. You know what I mean? So, same with this, if you call this an ester, you're not wrong, you're just not being specific enough to say that it's a lactone. But you're still right, that's an ester. That has an oxygen right next to it. This one is trying to trick you, it put a carbon before the oxygen. So, that one's not an ester. Okay, acidity of amides. Let's see. Amides are comparable in acidity to alcohols, which is interesting because I don't think amines are. Where's our pKa table? I meant to have that pKa table like in every slideshow after this. No, where did it go? pKa table. Oh, where is it? Oh God. Okay, so. Yeah, okay. So, you know how we've talked about this before, when we're talking about pKa, it's very specific which hydrogen we're talking about. So up here, ammonium ions, if we're talking about NH3, NH3 is a good base. We know that because its conjugate acid, NH4+, has a pKa of around 9.4. That's, yeah, where's my, oh, I guess I cut it off, but like, yeah, these are good. These are good acids, right? So 9.4, that's a pretty good acid. That's kind of a lowish number. Are these like not? Okay, no, they are. They're better than phenols, which are better than most other alcohols. When we get over to ammonia, if we're just talking about NH3 or an amine, so R and H2, when we talk about this guy trying to be an acid, we're talking about removing one of these hydrogens to turn this into one hydrogen and two lone pairs and a negative charge, right? This, 36, doesn't really want to happen. Like an alkane doesn't really want to happen, this really doesn't want to happen. But when we put a, where is it? An amide, when we have an amide, so we put a carbonyl group right next to our amine, all of a sudden, our pK is 15, not 36. 36 is like, hell no. 15 is like, okay, that's like alcohols? That's, like, you can do chemistry with that, definitely. You can get that to, like, be deprotonated for chemistry to happen, right? So, is anyone looking at this, anyone tell me why this is a better acid? This can get deprotonated more easily than this.
Resonance stabilized?
Yeah, so better acid means more stable conjugate base, right? So if this is a better acid, that means this is more stable. this is more stable than this, and that's because we can do resonance here, so it's not just a negative charge on a nitrogen. We've got, like this, we've got some resonance going back and forth. So there's some negative on the nitrogen and some on the oxygen. So, yeah, these guys have a normal amide, acetamide is going to be 15 to 17, but you go into benzene sulfonamide, that's a pK of 10. Well, that's because we know that this, the ring and the SOO is a really good leaving group. And then if you get into these guys, there's, you've got all of this conjugation back here, and this one, so you've got like, this has 2, so you get like a 9.7, 8.3, you get more and more reactive. Yeah, so the more resonance stabilization you can do, the more reactive or the more acidic that hydrogen's going to be. So, acidity of imides. So we kind of looked at that right here. This guy's an imide, right? Which is why it's not in the 15 range. It's 9.7. Well, these guys both, right? Those are imides. They've got 1 carbonyl on each side. So you can resonate both directions. So their pKs are even lower. What is true again at when pH equals pKa? What equals what? Do we remember? When pH equals pKa, that's when your concentration of your acid and your conjugate base are the same. So that's kind of, that also kind of gives you an idea of, like, helps you translate pKa's to like acidity, because, okay, so we don't have a whole lot of pKa's under 7, right? But still, just having equal concentrations of those at like any pH that's not really, really low, like, I mean, if you could get a pH of 60, if you could somehow manage a pH of 60, you would finally get an equal amount of alkanes and deprotonated alkanes, right? You never will, but like theoretically. So when we go to like 15, 16, those are totally possible. Like, yeah, it's basic from when we're talking about, like, from when we remember Gen Chem, but like totally possible pHs. And so you can hit equilibrium there. Let's see. Water insoluble amides. So if these guys are not soluble in water, they're not going to react with aqueous solutions of NaOH to form water-soluble salts, which is interesting, right? Because our carboxylic acids, they do deprotonate to form water-soluble salts, whether they're soluble in water to begin with or not, right? Amides, they don't do that. Okay, that's saccharin. It's an artificial sweetener. It's, I mean, is that really an imide? That, I don't think that okay, I guess loosely that's an imide, if it doesn't have to be next to 2 carbonyls, but it has to be next to 2 somethings double bonded to an oxygen, I guess. I do not remember which artificial sweetener saccharin is, though. Yeah. If someone wants to look that up, if you're interested in it, let me know. Okay, acidity of sulfonamides. Okay, good. We are almost at 8:45, but also this is the last slide before we start doing chemistry on the board with arrows and writing things. So, acidity of sulfonamides, they're derived from ammonia and primary amines. Sulfonamides, these guys, they're sufficiently acidic to dissolve in aqueous solutions of NaOH or other alkali metal hydroxides, some sort of something OH, and these guys form water soluble salts. Why? Because hella resonance, right? Acidity is accounted for by the resonance stabilization of the resulting anion. So yeah, these guys do all the resonance if you deprotonate them, and you can deprotonate them as long as you stick it in high pH water. You stick it in very basic water. Okay, let's take a break.